as you can imagine, I am thrilled to be back with you and to see all of your faces again for one last week for the semester. As is customary for this class, we've got one final figure for our semester to learn a little bit more about. Do any of you in the audience have an idea of who this is? If you do, just shout it out. Admiral Grace Hopper. She was a rear admiral in the US Navy and another pioneer of computer science. Born in 1906, she died in 1992 and really created the idea of programming languages that were machine independent. We've looked a little bit in this class about languages that weren't machine independent, our assembly languages that depended very heavily on the particular kind of computer chips on which they were being used. Grace Hopper's idea was that instead of having a programming language that only has instructions that correspond to the specific machine on which you're operating, a programming language should be portable. So if you take it from your phone to your laptop, which might have very different chips inside it and might work very differently, you should be able to use the same programming language. Even more than that, Grace Hopper was inspired by the idea that programmers should be able to write in something approximating English. Maybe not quite the conversational English that you and I are used to, but at least something that is akin maybe to the C programming language, which has many words that we're familiar with. From this idea, which she wrote quite heavily about in her early works, stemmed a programming language, COBOL, for which she wrote one of the early compilers. Later on, the COBOL programming language turned into the C programming language and a whole other family of languages. And so what we're doing today is very directly related to the ideas of Grace Hopper. Also related to this, Grace Hopper was the inventor of was one of the inventors of the A programming language, which eventually led to B, which eventually led to C. So there is some history there, and then C++, which many of you have also heard of, is again a variant building on from C. C with a lot more features. So what now? What do we do? Well, I'll take some ideas from you guys because maybe I'm fresh out. What do we do now that we've learned all these algorithms? You've packed full of different cool ideas. What should we do next? And so if you've got a couple seconds, let's open up Poll Everywhere and see what you think. So what should we do in class this week? We've learned a whole bunch of algorithms. What's left for us to do? Apply some algorithms. Okay, so find some interesting problems to use them for. Other ideas? Is anyone in favor of just ending class 3 days early and going home? Yeah? Okay, so we've got a few of those. End class early. Okay, any other votes? We have, Nicholas says we should categorize and synthesize. So I guess that's a reasonable option. Any more before we go ahead with this one? So we could sort all the algorithms we've learned in a couple of different ways. We could sort it by the problem type that they set out to solve. We could sort them by complexity class, so how long do they take to run? Or we could sort them by the way they were designed. And we're going to look a little bit at each of these three different ways of analyzing algorithms. So the first is fairly intuitive. What are the different problem types that one could solve? This is going on Wikipedia and just looking up list of algorithms. And the way this list of algorithms on Wikipedia is organized is by the kinds of problems that you're able to solve using a given algorithm. So perhaps you're looking at graphs, which are a way of representing connections between things. Maybe you're looking at sequences. It goes on and on. Physics, chemistry, biology. There are algorithms for this, that, and everything. And while I'm sure continuing the class by going through the list and looking at every algorithm people have written would be fascinating for some of you, others of you might get put to sleep fast, and we might have a very low attendance rate for the remainder of our lectures. Oh, here we are. Here are a bunch of different applications that we could go before we move on. So we could look at the best way to plot train routes across America, the best way to model animal behavior, how to fill in holes in damaged photographs, and these all are wonderful and useful things and super interesting, but perhaps they don't give us the biggest bang for buck in terms of the time we spend in this class now. If you want now with the skills you've learned, you could go and actually do any of these things. You just look up the algorithm and implement it. But as well, we were more interested in this class of figuring out the how and whys of algorithms. And learning a lot more of them won't necessarily give us that. So we'll move to the design techniques, the way that which all of these are made. And there are a few broad classes that one could look at when attempting to synthesize the different types of algorithms that there are. There's divide and conquer, optimization, generate and test, simulation and randomization, and approximation, just to name a few. Now, these categories aren't hard and fast. If you go to a professor of algorithms and say, I know the 7 categories of algorithms, they'll give you a weird look. These aren't the actual way that the universe is structured. This is just one helpful way of thinking about some of them for the purposes of this class. And we'll go through a few of these in particular that are more recognized. The first of these is generate and test, which is pretty much what it sounds. And we'll stay on this one for a moment. Generate and test is look at all the possible solutions for the problem that you're trying to solve, look at them in a particular order, and then check each one of them in turn. So for example, if I want to find out, is there someone in the class whose birthday is October 27, I check through the list of everyone in the class and ask, is your birthday October 27, et cetera, et cetera, et cetera. And when I find the person whose birthday it is, really? It's your birthday's October 27? Howdy! Wonderful. That was very easy. So we do have someone in the class whose birthday is October 27. What a lucky pick by me. But in many cases, this is perhaps not the best strategy for our problem solving. A more complicated example might be, what is the fastest way of drawing a train route that connects Sydney, Canberra, Brisbane, and Melbourne that doesn't go through any houses and connects each city but not all of them to each other. And you could draw a lot of different routes that would be valid. Maybe one goes around the coast of Australia and then kind of loops. Maybe another has some direct lines, but obviously the train lines can't cross itself because the trains will run into each other. So you could keep drawing all the different possible routes, and there are a very large number of them, and try and find the one that's the most efficient, say the most fuel efficient. But this is going to be pretty tricky because, firstly, the solution, it's not clear how to generate the next route because there are so many of them and there are so many different ways to draw them, and also there'd be a lot of them to check. So this leads to our kind of broad question about this category is, what are the limitations of generate and test? And we'll go to the audience for this one. Just conceptually, what are my challenges?
I'm guessing it's kind of like the same limitations when you do linear search because you have to kind of like do it for every element. So in this given sort of like problem, there might be a lot of elements and you have to check through all of them.
So that's a really good point. Keep holding the microphone for a second. If I have an array of length n and I'm looking for something in the array, what the runtime was?
Okay.
Yeah, and so in that case, our possible solution space. Oh, I've lost that. So in that case, the solution space is pretty small. It's bounded by the number of elements in the array. What about if I want to find all the different ways of coloring a map of the states of the United States using 3 different colors?
Of n squared, n cubed.
Because, do you want to explain that a little more?
Because for every, like for example, if you have n NOA and you fix it as one color, you have n minus 1 sort of like possible combination. It's like a recurrence problem, and then wait.
So for each state, how many different ways are there of coloring that state?
There's 3 possible colors.
Yep, and so that would give me, and then I'd have n minus 1 states left to color. So the next state, how many ways do I have of coloring it?
Oh, so that would be 3 to the n actually. Oh, 3 to the n, right?
What do you think?
Yeah, because you have like 3 choices for the first item, 3 choices for the second item, 3 choices for the nth item. So 3 times 3 times 3, so 3
Yeah, so that makes sense. Now, this seems rather silly. Why would I care about all the possible ways to color a map of the United States of America with 3 different colors? But it turns out if I impose another rule, and let's say that this rule is that no 2 adjoining states can share the same color, and I ask you, is there a way of coloring that map? the problem becomes a lot more interesting suddenly, and yet you don't know how to do it ahead of time. And if we're using the generate and test strategy, we're still going to have to look through some of these 3 to the n possibilities in order to find our map that matches this coloring. And this problem turns out to be very interesting, the particular map one. We'll return to it a little later in our discussion, but thanks for this so far. We see that generate and test has this limitation in that if our search space gets large, our runtime for our algorithm also gets really, really large, and that's not a good thing. There are some other limitations of generate and test as well, in that the search space might be non-enumerable. What do I mean by this? It means that there's not an obvious way of figuring out what the possible solutions are. So with something like the map, it's very easy to figure out, okay, if I've tried this combination of colors, this is the next combination of colors I can try, there's another combination here. But with the train example, the train tracks, it's not exactly clear how to generate another track that goes from there to there. I mean, there are potentially an infinite number of ways of drawing it, because you could draw a slightly different angle, or you could draw slightly different points, and so it's not clear how enumerable it is. It's not clear how you can generate a list of the different possible tracks. So generate and test doesn't work very well for that example. And it might also be difficult to figure out what's the right order in which to check tracks if I'm looking for the best one, because there's no clear ordering of different maps that you've made. This takes us to our next strategy, which we've used a whole bunch of times in the course, divide and conquer. To understand what divide and conquer is, we're going to look at one of our last 2 sorting algorithms. And yes, we are back to sorting. So hopefully you can dig out of your memory from that earlier lecture all our bubble sort and insertion sort, and we can compare this new one and see how it goes. So to understand merge sort, I had some props planned, but unfortunately they were in the suitcase that disappeared in today's flight. So we will look at this video instead, and I'll restart it. The way merge sort works is we have a starting array. We're going to split it in 2. Split it in 2 again, and keep splitting in 2, and you've seen this pattern before. Split it in 2 until we've only got 1 item that we're currently looking at. After dividing it into portions that have just 1 item, we're then going to combine these portions in a way such that each portion of 2 is now sorted, because a portion of 1 is obviously sorted. Then we have this operation called merge, which takes 2 different arrays, 2 different subarrays that are sorted, and puts them together. And so that's the process that you're seeing here. We have these 2 halves, and these 2 halves are being combined in something called a merge. Let's look at the code for this. I'm not going to spend quite as much time explaining it, because we have already looked at a number of sorting algorithms that are very, very similar to this. In particular, does anyone remember one algorithm that looks pretty similar? Is there any of the algorithms that looks pretty close? Quicksort. Why do you think quicksort was the similar one? So this idea of cutting into smaller and smaller pieces. And this is essentially what divide and conquer is all about. Divide and conquer is take the problem that's big and kind of tricky to solve, sorting something, for example, and then find a smaller version of it that you know how to solve. As we said in the very early lecture on sorting, we know how to sort an array of 1 element because, well, 1 element is already sorted. And we kind of know how to sort an array of 2 elements because you just figure out which of the 2 is larger and then place if we're doing from smallest to largest, you place the smallest one first and the larger one second. So we know how to solve this problem once we've broken it down to a really small portion. And then what we need is some way to combine our solutions from the smaller one into the larger one. And keep thinking, while in the back of your heads, are there any other algorithms that we visited that apply this kind of fundamental principle where smaller solutions make up larger ones? And there are a whole lot of them. So when I ask you in a minute, I expect you to have a few answers. So we've broken up our large array into small pieces. when we make sure the small piece is sorted, and then we combine small pieces together to create larger sorted pieces and larger sorted pieces until we've sorted the whole thing. This gives us an algorithm that actually looks pretty similar to quicksort. This is merge sort. So if you have one element, just return it. That element is already sorted. Otherwise, figure out the midpoint of your array, and I'm missing floors and ceilings here, but you can add them in as you need. Of course, C automatically takes the floor because it does integer division, truncates off the end, and so you get a floor. But if you're writing this formally, you might want to put it in. So take the midpoint, and then run merge sort on the small half. So solve it not the small half, solve it for the left half, solve it for the right half, and then when you have both pieces solved, merge them together. And we haven't defined what merge means yet. We're going to do that on the next slide. But this is the entirety of merge sort. Just like quicksort was very short because it relied on us having a base case and building up from that base case, so too is merge sort very, very similar. In quicksort, though, instead of having the merge down at the bottom, we had partition that was above. So we'd partition it and then do quicksort on both of them. And that's essentially the only difference here, is we've swapped out our partition for our merge, and instead of doing partition before, we are doing merge after. Let's see what the merge looks like. This is our merge function. It takes two arrays that are unsorted and is going to combine them together, two sorted arrays, and is going to combine them such that the combination of the two is also sorted. And you can think ahead, if we can do this for any arbitrary two pieces of the array, if we keep combining pieces and making sure that the pieces together are sorted, once we've done this for all the pieces, then we are going to have an overall sorted thing after we've done this for every possible piece. And because our strategy is divided in two and divided in two and divided in two, you can also start to get a sense of what the runtime is going to be if you think about it carefully. Don't worry, we'll get there for a full analysis. This is what it looks like schematically. We have an auxiliary array, and we're going to call that T, where we're going to copy over all the elements from one of the halves. And we have the other side that's sorted as well. So T up to mid is just a copy of what was previously in 0 to mid. So we had these two halves of each of which was sorted, but they're not sorted together. They're not combined sorted. They're only each sorted within themselves. Then what we're going to do is we are going to merge these two together, taking all the pieces of each, such that when we combine them, the overall thing is sorted. Unfortunately, my little diagram is lost in Qantas's baggage handling somewhere, my thing for the iPad. So we'll have to give that a miss. But the general idea here is to the first line creates an auxiliary array T, and inside that auxiliary array, take everything from the left side, copy it into T. Why are we doing that? Well, when we're going to start in our merge process, we're going to be overwriting elements in those locations where originally there would have been the previously sorted stretch. So in the left half, we've sorted the left half, we've sorted the right half, but they're not sorted together. And because we're going to start overwriting those things with the final order, we need to make a copy of those items such that we can then fill up that portion of the final array with the correct items overall. Then we have a bunch of pointers that are going to point to different locations in the left half and the right half to tell us which item in the left half which item in the left half we're looking at and which item in the right half. The idea is if we start looking at the beginning of the left half and start looking at the beginning of the right half, knowing that they're both sorted, if every time we check which of the two is bigger, that tells us what the next item in our overall ordering should be. So let's say that this is the number 1 and that's the number 3. And I'm trying to figure out, if I'm going from smallest to largest, which of these two items should be the one that I copy back into the main order. So if I have 1 and 3, what do I do? Vincent, you've already answered me a little bit this lecture. So if I've got 1 and 3, I'm trying to go from smallest to largest. What do I put into the final order first? Okay, Albert says 1. And so we copy, because 1 is smaller than 3 and our final order is smaller than largest, we copy the 1 over into our final array. Okay, so now let's say we have 7 and 3. Which of the two should now go in, and not Albert and not Vincent? So now the 3 should go in because the 3 is smaller. So we copy the 3 over, and we move up our pointers such that we move on from the 3, and this is still pointing to the 7, because the 7 hasn't gone in the final order yet. Now, if this is 9 on the right hand, and if this is 7 over here, now 7 is smaller than 9. We copy the 7 into the final array, and we move that pointer along. And that's the whole strategy here, is while our pointer on the left side is still in the left side, and while our pointer on the right side is not at the end, check which of the two is the smaller one, and copy that one into the next position in the final merged copy. If you copy from the left side, move the left side's pointer over. If you copy from the right side, move the right side's pointer over. If you've reached the end of the left side and there are still items left in the right side, just copy them in. And that is the entirety of merge. Now, obviously, it's going to be a little tricky to understand from my fingers moving around in the air. But once we get our technology back in order and my suitcase back from the airport, hopefully we can revisit this with a bit more of a clearer diagram. If not, as with all the algorithms in the class, the best way to understand it is by drawing it out yourself with a few samples and working through it. Oh, now it wants to play. There we go. Anyway, so we will take a short look at the Mergesort code. Just give it a quick run, because it is almost the same as things you've seen before, so there's not too much need to belabor the details. It needs the sort scaffold file, which we've already seen a whole bunch. And then the actual merge sort function itself is very, very simple. As we saw in our pseudocode, it's essentially 4 main lines plus our base case. So find the midpoint, do merge sort, and then merge the two sides. And there are a few variants of merge sort, different ways that you could implement it. And our merge function takes a few more lines of code, but some of this is just commenting to help you understand it. I encourage you to download this code, give it a run for yourselves. The links are in the slides. So let's run it over here just to take a look. How many comparisons does merge sort need? So here's our normal runtime analysis. We're not going to do best case, worst case, and average case. We'll just look at the average case on this one and the worst case. Thinking back to the structure of our algorithm, very similar to quicksort, we have our 2 recursive calls. Those are 2 times t of n divided by 2, because in each recursive call, we are dividing this in half. Now, in the worst case, it might be the case that anyone know what will happen in the worst case? Is this going to be like quicksort, where we're going to sometimes have half of it that's like not actually a half, or is merge sort always going to divide them into equal halves? Think of the code, the pseudocode. Angel, I see you're nodding. Does that indicate that you know what's happening? Yeah, so unlike quicksort, where our partition function would sometimes give us a partition where just it was one element and then all the rest, and those were our 2 halves. With merge sort, we're always splitting it right in the middle, and you can always split it in the middle. Sometimes it might leave you with like 2 and 1 because you have an odd number, but more or less we're going to get an n on 2 split every time. And so unlike quicksort, where we had our worst case where we had to analyze this weird split, in merge sort, our worst case is always still going to be this even split, accounting for the the floor of, sorry, the seal of that, the ceiling. So we get our 2 times our recursion relationship there. And in each of those steps, we also have to do n work for the merge, because the merge, we're going to have to look at all the elements that were passed into that particular step. So that'll give us at least n. Then we have our base case. So if t of n, if n is equal to 1, or n is equal to 0, then we don't really have to do anything to sort it, just return immediately. And so our base case is going to be 1. With a little bit of mathematical finagling, we're going to get our n log n worst case, which is better than our than quicksort, which had n squared. Does anyone have an idea why we might still prefer quicksort to merge sort, even though the worst case for merge sort looks better? It's n log n worst case as opposed to quicksort, which was n squared. Leto, do you have an idea? Pass it back.
Not 100% sure, but is it because the average case for quicksort is still better?
So the average case formally is still going to be n log n. And what do we actually care about when running the algorithm on a computer? Do we care about the big O time more than anything else?
No, also space.
So we care about space, but that's not going to be the distinguishing feature here. When I actually go and run one of these algorithms on my computer, when I've been typing things in class, do we measure the theoretical running time? What are we measuring when I look at my watch?
Not the theoretical one, but what it actually is.
Yeah, what the actual runtime is on a real set of data. And so it turns out that quicksort tends to be really good at a lot of normal types of data that people throw at sorting algorithms. And so quicksort, or variants of it, are very frequently, although not always, what is used in real applications as the default sorting algorithm. If you're going to be sorting really, really huge stuff, you should pay close attention to which of the sorting algorithms you're picking and how it fits your data. But it's worth also knowing that these formal trade-offs are also not necessarily what maps out to being the right choice for the real world. The right choice for an actual algorithm that you're using in an application is going to be much more sensitive to your data and to how much memory you have, considerations beyond just the formal big O runtime. Thanks, Leto. Oh, and so we actually have to do this analysis. I almost forgot. So looking at our runtime, at our recursion relationship, so in our base case, we're always going to have, I think there might be some minor errors here. It's still going to work out roughly the same. At the top level, you're going to have n, because this is before we've done any recursion whatsoever. If we look at our recursion relation, we have n plus 2 times whatever the next one is. That's our first n. Then we have 2 times n on 2, and each of those, because each of the two sides of each of the two recursive calls are each going to contribute n on 2. So that's 2 times n on 2. And then we're going to halve n on 2 again, and each of those halves are going to give us a contribution of n on 2 on 2, et cetera, et cetera, et cetera. So if we write out the sequence of terms, we get n times 1 on 2 to the 0, plus 1 on 2 to the 1, plus 2 to the 2, et cetera, et cetera. Swapping in for our k equals log n, and that we're just using, it's by definition, we're creating a variable k. We know there are k terms in that sequence, and if we just multiply that out, that'll give us log n. So we get n on 2 by log n plus n, and this is an upper bound for t of n, which is fine, because with big O is itself an upper bound, and so the fact that we've been a little imprecise here is okay. And so we get n log n worst case because we're dropping that n as well. And this derivation is pretty much the same as the earlier derivations from the class. So even though I'm working through it much, much faster and not going through it in as much detail, if this derivation is a little confusing, go back to the earlier lecture and see how we did it in a little more depth. One interesting challenge that you might have with merge sort is trying to do it without having to build this auxiliary array, this second copy of the left half of the array that we made in order to stop it from being overwritten. And the question is, can you do that while still preserving the n log n worst case running time for the algorithm? Now, there are a bunch of quite clever solutions that attempt to do this, but it turns out it's really hard to do, both in terms of writing it out formally and also in terms of implementation. And you make some improvements, but it's definitely going to be a bit slower than the version of merge sort we had here. While you may be able to get away with just large constant factors, I don't remember exactly what the state of the art is, it does turn out to be a very tricky thing to do. If you're interested in learning more about this, just type in merge sort on Wikipedia, and I'll give you a whole section on like the state of the art advances on merge sort, and there's still work being done in this area. So just like with all the other algorithms that we've been studying, as much as it seems like, wow, these are old and venerable algorithms that have been around forever, there's still plenty of room for people like you to pick, you know, maybe I'm interested in string repeats, or maybe I'm interested in sorting, or whatever it is that you happen to find fascinating with algorithms, and making small advances there and learning about what's really happening today and what are the challenges that people are facing today. So that's another, I think, exciting thing to think about this week as we're starting to wrap up the class, is what are the boundaries of the algorithms that we've learned about, and what are the places where there's still a lot of room for growth. So Moffat's wisdom from his slides and also from his book is this brief summary of the difference between merge sort and quick sort. So quick sort is hard split, easy join. The partition bit was kind of complicated, figuring out which items should go in which. And then it was easy to combine the two. You just literally like slam them together. Merge sort was different. It was very easy to split. You just split it in two. And then it was the join that was more complicated, where you had to follow the pointers. And so this is conceptually, I think, a really useful way of thinking about it, and not the way that I first thought about it. But I think the best way of thinking about this algorithm is kind of conceptualizing the two of them this way. And if you think about it in this form, it should also be easier for you to implement it from scratch. If someone like comes up to you on the street and goes, Yara, I'll give you $50 if you can, on this napkin, write down merge sort for me, thinking about it this way might help you be able to win that $50. It hasn't happened to me yet, but every time I walk down the street, I'm still hoping that someone will go like, Dr. Connie, I see you there, write down merge sort for me. Another famous problem that is in this divide and conquer paradigm, which is again this split, find the easiest, find something small, find an easy solution, and then combine. This is subset sum. And like the three-color problem that we talked about, this one is pretty devious. So the question for subset sum is looking at this set of numbers, or any large set of numbers, is there a subset of them that adds up precisely to some other number k? And in this case, let's say it's 1,000. Can you find me some of these numbers that together add up to exactly 1,000? And I can see some of you already trying. Does anyone have a solution? I would be very impressed if so, because not only would your addition skills have to be very fast, but you might have had to try an awful lot of different combinations. So the insight here to generating an algorithm for this that is fairly easy to write is that each one of these numbers is either in the final combination of numbers that adds up to k, or is not in the final set of numbers that adds up to k. So like 787 over there, 787 is one of two things. Either it makes up part of the sum to 1,000, or it doesn't make up part of the sum to 1,000. And so we can use this to try all combinations. Our algorithm for solving subset sum is really, really simple, but kind of deceptively so. So the first case is if you've just added a number to your sum, and so what we're going to do to figure out the sum is every time we add a number, we're going to subtract that number from our target. So if our target is 50, and you've just selected the number 50 from the pile, take 50 away from the target is now 0, and so you know that you've reached it exactly. If the target is 50 and you have the number 24 and the number 26, if you add 26 to the pile, take 26 away from the target, you have 24 left. You need 24 to go. And then when you add 24, you get to 0 again. you know you found that combination of numbers adds up to 50, because with each number you take away that amount from the target. So if your target is now 0, you've reached it, congratulations. If there are no numbers left in the array for you to look at that you could possibly add to your sum, well, then you have failed, because you still have to get to your target and you have no numbers left to choose from. So those are our base cases. Then we have our two recursive calls, which are breaking this down into smaller problems. We want to check if either of these are true. So the first one is the number, if the number is in the set. If the last number in our set, so let's make this a little more concrete by going back a slide, is 787 in the final combination of winning numbers. If it's in the final combination of winning numbers, well, we should make our array smaller, because the list of numbers that we can now look at doesn't include 787. We've already considered it. But our target, we should reduce by 787. We should reduce it by the amount of the number we're considering. So that's our first one. In the second instance, we are excluding 787. But because we've excluded it, we can also allow ourselves to look only at the remaining numbers in the array. So we're still going to make n one less. If we keep repeating this process, n is going to get one less with each of these checks. Eventually, we're going to have checked each number, both conditions, if it's in or if it's out. Here is our test array, trying to get to 1,000. N is just the size of the array. And you can see that this is pretty much the same code we had above. Let's see if this one will compile. Okay, maybe I had some errors in the other one. I'll have to check that out later. And subset sum returned 1. Subset sum returned 1. It was able to find it, so there is a set of those numbers that adds up to 1,000. Now notice that in this particular version of the problem, we didn't return which of the numbers are in it. With a fairly trivial modification that you should all be capable of, you'd be able to modify this to return the numbers, but it does make the code a little uglier, which is why we didn't do it now. It doesn't increase the running time. It increases the storage time a little bit, because you have to keep track of which numbers you've seen for any given recursive call, but it isn't conceptually very difficult. The only other thing I'd really add about this example is that subset sum is really, really, really inefficient. Much like we have an exponential runtime, much like what Vincent was talking about before with our 3 coloring problem. And so as much as we could solve it pretty easily for this small example, if we gave it a large example, which I haven't pre-prepared one, it would take longer than the age of the universe to solve and to tell us, well, in expectation. So subset sum is one of those very nice, easy to write, but difficult to make efficient algorithms. The other thing about subset sum is that it takes a lot of recursive calls, and we know when we do a lot of recursive calls, we're going to get stack overflows if we make too many recursive calls. We can always get around this by using a stack data structure instead of the operating system stack, but this still only gets us so far. We could rewrite it iteratively, but this only gets us so far. What we really care about for optimizing this program's runtime is how many possible combinations of items are there. Because we're looking through all the combinations of items, what's going to matter for us is how many combinations there are, and that's not something that we can improve by improving our programming. So turning to Wikipedia again, or mathematics, the order of the power set, which is the set of all sets, which is all the different combinations that you could possibly have, is of size 2 to the n for n elements. And this is very sad, because 2 to the n is a very, very bad runtime, because if you make n just a little bit bigger, 2 to the n grows really, really quickly. So my laptop can do 2 to the 38 operations in a reasonable amount of time. I haven't given a try recently, and depending what those operations are and how optimized it is, but that's doable for my laptop. 2 to the 40 is kind of pushing it for a computer, but you could imagine like supercomputer or an academic cluster could reasonably do 2 to the 40. 2 to the 50, maybe a team of professors with all their computers combined, a few $1 million worth, could probably do 2 to the 50. If you're the NSA, you could probably do like 2 to the 55 operations. And by the time you get to 2 to the 128, you're talking about every computer that will exist from now until the death of the universe, all working together from now until the death of the universe, probably couldn't solve the problem. And so as this problem gets large, the time that it takes to solve it grows really, really, really quickly, which is very unfortunate. So is there a better solution than this try all combinations one? This is one of the most fundamental problems in computer science. This is known as the P equals NP conjecture, for which there is a $1 million prize. There are a lot of other problems out there that are kind of similar to subset sum in that if you can solve subset sum, you can solve these other problems. And if you can solve these other problems, you can solve subset sum. If you find an algorithm for one of them, there's a way to convert the problems of the other types into one that you could solve using this one special algorithm. And so if you can come up with this algorithm, you essentially solve this major conjecture in computer science. Problems like these form part of what we call a complexity class called NP-Complete. And if you want to learn more about this, I think models of computation probably teaches you. Yeah, there's a third-year subject in computing which really explores this a little better. Now, when Vincent and I were talking before about the maps and the 3 colors, this is another example of an NP-complete problem. It turns out that map 3 coloring and subset sum are very closely related to each other through this type of complexity class. This entire class of problems are quite easy to check a solution if you've got one. There's a process that you can very quickly and easily run to know if you've got the right solution. For example, if I give you a large list of numbers and ask you, is there a set of numbers that adds up to 1,000 in there? And then I give you the set of numbers, you can both check that the numbers I've given you were part of the original list, and you can check that they add up to 1,000 really, really quickly and easily. Same thing with the map. If I give you a version of the map that's colored such that no 2 adjacent states have the same color, and I give you the coloring for every state, you can check that very, very easily. But to generate a correct map is really, really hard. And so this is one of the fundamental features, is these are problems that are easy to check and hard to solve. Very, very hard to solve. And we say that the problem is to find an efficient algorithm that solves it. Not just an algorithm. It can't run in exponential time. It has to run in polynomial time, which means big O of some polynomial. And remember, a polynomial is like an to the 3 or an to the 4 or an to the 5 plus bn to the 2 plus cn to the plus cn plus d. As long as it's a polynomial of some sort, that counts as a polynomial time algorithm. And that is the holy grail for finding algorithms that would solve this complexity class. However, we do have such reason to believe that no such algorithms exist, and that this class of problems really is fundamentally difficult. There is this beautiful paper, which is, if you have a bit of free time, it's not part of the course, I would highly encourage you to read, by Scott Aaronson, who talks about why this tells us something about the fundamental structure of the universe, and that if these problems were able to be efficiently solved, the universe would look nothing like the way it does. All of physics would be different. And I'm going to end today with one quote from Scott Aaronson. I'm not sure if this appeared in the paper, but he certainly said it. If P equals NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Everyone who could recognize a good investment strategy would be Warren Buffett. And this is fundamentally true. What this P equals NP conjecture tells us, that if such algorithms exist to solve these things efficiently, then there is no real gap between finding, then for any problem in the world, no matter what the problem is, between finding a solution and recognizing a solution to the problem. And this goes for all the hardest problems in the universe. Making mathematical proofs, writing beautiful music, recognizing whether something is artistic or not, all of these things that are very, very difficult to write algorithms for. If we could find very fast and smart and efficient algorithms, it would take away a lot of the beauty in the universe and the beauty in life. So this idea of algorithmic complexity plays a really deep role in what it means to be human, and that's what I'll leave you with for today. Thanks very much, everyone.